Why don't we begin? So this mini course is going to start all the way back in the 1800s with classical Hurwitz theory, and it's going to get all the way to 2022 with kind of the technology that Dhruv, among other people, has been helping develop that is giving some interesting new perspective, right? So it's clearly going to be kind of a little bit fast, hopefully not too furious, but I encourage, everybody to get out of this mini course what you need. No, I don't expect all of you will become Hurwitz theorists, but it's a good sort of area of mathematics to have in mind and know a little bit about because of how it connects to many other areas of mathematics and because of some of the ideas that it uses, right? I encourage you, if you haven't downloaded the notes yet, to look at the notes. In those notes, there's way more information that I'm going to be able to cover as I speak. But again, the idea is that some of you might want to read a little bit more about the basic stuff, and some of you might want to skip right ahead to the more advanced stuff. It should be all in the notes. So please feel free to use them as you can, and to use myself and Vance and everybody else during whatever free time we have to, again, get out of this mini course whatever is best for you to get, okay? So, all right, so now my goal is to sort of put to sleep all the experts, right? And start with just very basic ideas, because I'm not assuming that everybody has even seen what a Riemann surface is, right? So we will not dwell very much, but, I'm going to say that a Riemann surface is a compact, complex, manifold of dimension 1, right? So it's some geometric space such that for every point you have an open set that can be identified with an open set of C, the complex plane, and such that when two open sets intersect, you get some transition function. This is holomorphic. This is a holomorphic function. Okay. You get immediately as a consequence from the Cauchy-Riemann equation implies that, well, these are, surfaces, because being identifiable with the complex plane means that you have real dimension 2. And the Cauchy-Riemann equation implies that these are orientable surfaces. And so we know that topologically orientable surfaces are completely classified by one discrete invariant, which is the genus, right? So there is the first discrete invariant, so any Riemann surface is a donut with a bunch of holes, right? And G is the number of holes. Okay. So this is really all we'll need so far about Riemann surfaces, right? We're going to be concerned about maps of Riemann surfaces. And maps of Riemann surfaces, again, if you've never thought about had a manifold course, then maybe this is a good time to spend 10-15 minutes this afternoon figuring out what it is. But it's one of those things that once you've done it once or twice in mathematics, there's, what else can you do, right? I mean, we know how to, we want a notion of a map being holomorphic. We know what it means to be holomorphic when you have a map from the complex numbers to the complex numbers. You have two geometric objects that at every point can be identified with an open set in the complex numbers. And so if you have a function between these two geometric objects, it's going to be holomorphic at a point if, when you identify the corresponding neighborhoods and go all around the diagram, what you get here is a holomorphic function. Okay, if you've never seen this before, this might have felt like a tornado and you're a ping pong ball. But, let's talk about it this afternoon, right? So map of Riemann surfaces, you use charts to identify locally source and target with C, and then use complex analysis definition. And use. Okay, so maybe actually, let me draw a picture. I have a Riemann surface X and a Riemann surface Y, and I have a set theoretic function here, right? I want to say what it means to be holomorphic at this point, little x, right? Then what I do is I take a little neighborhood of x with a chart, and this gives me an open set in C, where 0 is the image of little x. And then I look at f of x, and I play the same game with f of x, take a little neighborhood and a chart C, such that 0 is C of f of x. All right? And then what I get is a function from here to here that I call the local analytic expression of my function f, and I'm asking this big F to be a holomorphic function. In fact, something a lot stronger happens because you're kind of free to choose your local coordinate system however you want. It's always possible, whatever the map of Riemann surfaces is, it's always possible to choose local coordinates here and here, such that, let's give names to these local coordinates. Let's say, let's call this local coordinate Z and this W, that this local expression is equal to, is very simple, is W equal Z to the K. It's a sort of a monomial function, right? And this K is another discrete invariant of maps of Riemann surfaces, right? So this is called the ramification order of f at the point x. Okay? And then what one shows, right, is that, there are only finally many points x in x which have ramification order strictly greater than 1. And these are called ramification points, right? Right, so my picture is that, all right, there's going to be some finite number of points here where the k is different than 1. Everywhere else, the map actually looks locally like a homeomorphism, or even like an isomorphism of an open set of C to C. Okay, so we call these red points here the ramification points. And we call their images branch points. These are the images of ramification points. Okay. And so if you pluck out all the branch points from Y and pluck out all the inverse images of the branch points from X, which means in particular you pluck out all the ramification points, but you might have to pluck out something more, right? Because not every inverse image of a branch point is a ramification point, right? There's a quantifier there. There exists an inverse image which is a ramification point, not for all, right? But if you remove all the bad guys here and all the inverse images of the bad folks here, Then what you're left with is a covering of connected spaces. And sorry, maybe I should add connected in my definition of Riemann surface, but I don't want to, because actually I will consider disconnected sometimes. But now let's just say that if I have a map of connected Riemann surfaces, then I remove these points, I'm left with a covering of connected topological spaces, and that has a well-defined notion of degree, which basically is pick any point which is not a bad point and look at the number of inverse images, and there's D inverse images, and this number is the degree of the function f. And in fact, yeah, question.
I just wonder if you could repeat what branch points are, because I can't read it.
Yeah, so branch points are images of ramification points. So there's bad points here or good points, depending on your moral standards, right? And then their images are branch points. And the name branch points comes from sort of historical reasons, because these are sort of like, what back in the 1800s people were doing. We're actually thinking about the inverse function out here, and that's where the inverse function is multivalued and it has branches, right? So like square roots, cube roots, kth roots in particular, right? So that's where the name comes from. Okay. So the degree is the number of inverse images at a point which is not a branch point. It turns out that you can actually compute the degree by looking at the inverse images at branch points as well, right? But with the caveat that every inverse image, you don't just count it once, but you count it with its ramification order, right? This is a little technical theorem that one has to prove, but you look above a branch points, you might have fewer than D inverse images, but these fewer than D inverse images have some of them have larger than one ramification order, and if you add all the ramification order, you get D. Okay? So at a branch point, let me make another definition. So the ramification profile at a point P in Y is the list, the unordered list of ramification orders of the inverse images of P, and the ramification profile is a partition of the degree. Okay. Great. Any questions so far?
And this is true for any f that's a function. It does not have to be like a polynomial or rational function.
Nope. This is any map of Riemann surfaces. Yeah. Absolutely. Cool. So now we have introduced basically all the discrete invariants that we need to introduce the counting problem that we want to count, right? So let me write a symbol, draw a picture, and H to G, degree D, eta 1, eta S, R. And let me draw a picture here. Okay, so I'm going to define this thing called the Hurwitz number. This Hurwitz number depends on a bunch of things. I'm going to introduce one by one, but we've seen them all, right? So first of all, D is the degree, so I'm going to count a number of maps or Riemann surfaces of degree D. Okay. H and G are the genera of the Riemann surfaces. Right, so I'm going to ask that X has genus H and Y has genus G. Eta 1 to eta S, these are partitions of the degree D, and they're going to identify ramification profiles for S points of Y. So what this means is I fix S points, let me call them P1, P2 to PS on Y, and when I want to say is precisely how many inverse images I have over each of these points and what the ramification order are, right? So for example, over P1, right, I've just, let's say that D is 7. Over P1, I have just one point where the local expression is W equals Z to the 7. Right? And maybe, and so then I'll say that eta 1 is just 7, right? If eta 2 is 4, 3, then I have 2 points, one where the local expression is W equals Z to the 4th, and the other one is W equals Z cubed. And I'm around Drew for 2 days, I'm already saying Z instead of Z. There's something. Okay. Then what are we missing? We're missing R. And so R is another set of fixed points. Let me call them Q1 to QR. And over these fixed points, I want to have what's called simple ramification, which means I have ramification, but as little as possible. What that means that instead of D inverse images, I have D minus 1 inverse images. So almost all of them are not ramified, and one inverse image is ramified to order 2, which is the smallest one possible, right? Or in other words, the ramification profile here is 2, 1, 1, 1, right? So I usually like to denote it this way. Like I have D minus 1 inverse images. Let's see if I even got this right. 1, 2, 3, 4, 5, 6, 7, right? I have 6 inverse images, 1 when I have sort of ramification order 2. Okay? So I want to count the number of maps of Riemann surfaces with all these discrete invariants. And like we always want to do, what we really want to count is isomorphism classes of this map. And like we often want to do as geometers, we want to count by weighting each of these maps by the number of automorphisms of the function f. Okay? So, and not telling you what an isomorphism of covers of Riemann surfaces, maps of Riemann surfaces is. I'm not telling you what an automorphism of map of Riemann surfaces is because I put them in the exercises, right? And again, it's like, how can I come up with such an idea? Well, you know, we're all mathematicians. We've seen the notion of isomorphism, automorphism in other categories, probably. So this is one exercise in like, what could it be? What's the natural notion? Okay, so, but once you figure out what the correct diagram that has to commute is, right, then this definition makes sense. Yeah, Alessio. Huh? good question. You're a little step ahead of me. So there is a few variants of this Hurwitz number. One is, sorry, you asked me if y is connected? So y is always connected in the sense that if you take y disconnected, then it's not really even a well-defined problem, right? Or it is, but it's multiplicative. But is x connected, right? And the answer is if you want, right? So there's two variants. There's one where you count just connected covers, and there's one where you count disconnected covers. And when you count disconnected covers, your advisor introduced the notation bullet, right? And so if you see a bullet here, then x could be disconnected. What? Absolutely. Absolutely. Yeah. You're preempting a few observations that I'm going to say. So give me 3 minutes and then ask me the question I haven't answered, but totally legit. Yeah. Okay. You see, yes?
Can you give me an indication of why we divide by automorphisms when we take some with respect to isomorphisms?
Yeah, so I think that the most natural and elementary way to motivate this is that once we will make a connection to an algebraic problem, an algebraic counting problem, this division by automorphism will be a very natural thing to do. A more sophisticated, sort of geometric answer is that we will want to interpret this number as some degree of some map of stacks. Stacks are horrible things or wonderful things, depending on your point of view. But the key thing is that the geometric intuition of a stack is you'd like to take quotient spaces even when the action of a group is not nice everywhere, so not properly discontinuous. And the price to pay is that when you have stabilizers, you kind of remember that the group got kind of quotiented out by some automorphism group. And that's precisely sort of like what makes this theory flow. Yeah. Okay. Yeah, Matt.
So if like eta 1 equals eta 2, and you switch between P1 and P2, those are different?
I mean, so those are the same Hurwitz number, obviously, but I am labeling P1 and P2.
So that kind of swaps.
Yeah. Okay. Okay. Let me add a couple more comments on this sort of like notation, simple stuff. So one variation, and I was in the middle of talking about, is like we could have x being disconnected. And why am I emphasizing this? So it's kind of interesting mathematics. So sometimes different versions are better for different things, right? So for example, one could say, well, the connected things are the things that we want to count, because then if you have a disconnected cover, it's really kind of some product of connected covers, right? So the atomic object is the connected count. On the other hand, once we will make the translation, again, to an algebraic counting problem, this will translate to a problem in the class algebra of the symmetric group, and this problem will be infinitely more natural if you consider disconnected cover. Also, when we write down the degeneration formula, it will be a lot more natural if you write disconnected, right? So it's kind of interesting how, depending on what you're trying to do, some things might seem more natural or more elementary. Another thing that, another convention, this was introduced by Goulden, Jackson, and Vakil, is if some of this eta have some parts that have the same number. So for example, let me say here, this eta is 2, 2, 3, right? I have two inverse images with ramification order 2 and one with ramification order 3, right? Then what we want to do is we're going to, we can certainly tell apart the point which has ramification order 2 from 3 from the 2's, but we cannot tell these two apart. So we're going to force it. We're going to call this, 2A and 2B. We're going to mark the 2's so that we can distinguish them. Right? Again, the effect here is that you multiply, whether you want to add this XOR structure or not, gives a multiplicative factor of the automorphism of each of the partitions. And the theory is more natural under certain aspects without these factors and less natural with these factors. Okay? All right, the last observation, yeah, Monty.
Sorry, I'm a bit behind, but like, can you tell us again what the R represented?
Yeah, so I'm going to answer your question and then also like connect to Alessio's slight unhappiness. So R is another sort of fixed number of fixed points on Y, where above these points I'm requiring what's called simple ramification. So D minus 1 inverse images. So again, one could say like I don't care about the R. I could just put all of these as 2 1-1-1s in the etas. But the fact that we have a sort of a minimal kind of ramification is important to play a special role. Now, the next observation is that all of these discrete invariants, I mean, of course you can choose them at random, but if you choose them at random with probability 1, that number will be 0, right? So all these invariants are determined, they're connected by what's called the Riemann-Hurwitz formula, right? So all above discrete invariants must satisfy the Riemann-Hurwitz formula. Which is that 2 genus of x minus 2 has to be equal to d times 2 the genus of y minus 2 plus the summation over all x's in X of the ramification of f at x minus 1. Okay. And again, if you've never seen the Riemann-Hurwitz formula, it's a beautiful formula which is fun to prove. And so in the exercises, I've put a couple hints for a couple ways that you can prove this formula. And you can prove it with just straight out topology or with complex analysis. Either one, it works. Okay, so if you pick invariants at random and this equation is not satisfied, you don't have any cover, so the Hurwitz number is automatically 0. Should I always write all these discrete invariants? No, right? I like to put them all out here at first, and then again when you're doing some theory, depending on which are the ones that is important for you to highlight, you might only write those and omit the other ones that are dependent, right? But I'm a fan of redundant notation, at least the first time we introduce it. Okay. Any questions? Yeah, Jay.
So why a simple ramification profile which you independently wrote down on the...
Why did I put it here?
Yeah.
Because I can. You're right, there's no particular reason yet, but you will see later, well, later today I don't know, because I think I'm going a little slower than I thought, but at some point you'll see again, some of the things is like, why are you putting all these indices? Why, because sometimes for certain aspects of the theory, you'll highlight something, you'll drop some others, that R can play a role that is important. Yeah?
So in eta 1 to eta s, you don't take simple ramification points.
The eta 1 to eta s can be anything you want, including simple ramification points. Yeah.
So the genus of x when x is not connected.
The genus of x when x is not connected is the sum of the genera of the connected components minus the number of connected components plus 1. And the thing is, like, you work that out by using the Euler characteristic instead of the genus to define the genus. Yeah. That's, yeah. Yes?
And then the other branch points other than those two items.
Oh, yes, thank you. Absolutely important. Yes, these are all the branch points, all the ramification points, right? So no other ramification. Other than above P's and Q's. Thank you. Absolutely. Cool. So, very natural definition. We figured out what the discrete invariants of maps of Riemann surfaces are, and then we said, okay, well, let's fix some discrete invariants and count the number of maps that we have. And that's a Hurwitz number, very natural. Now, just about the only Hurwitz number that I think one can compute using this definition is this one. Well, maybe there's a few more, but I mean, maybe let me say the only infinite family of Hurwitz number that one may compute is this one, which turns out to be 1 over d. Right? And how can I have 1 over d covers? Well, in this case, I have one cover, but this cover has a group of automorphism of order d. Okay? And again, it's one of the exercises I put in the notes to actually do this computation, because what this is going to force you to do is be really honest about the notion of isomorphism, automorphism of maps or Riemann surfaces. Okay? Good. Cool. Great. So now that I've told you a beautiful definition and that this definition is completely hopeless to do anything with it, right? Let's try to find some way around it, right? So we're going to introduce what's called, oh, sorry, let me say one more thing. So we've already seen here that maps of Riemann surfaces are what are called ramified covers, right? They're topological covers of y minus a finite number of points from x minus a finite number of points. Right? So when you have this sort of like kind of data, you call it a ramified cover. So every map of Riemann surface is a ramified cover. Conversely, there is a beautiful theorem by Riemann called Riemann's existent theorem that says that if you give me a topological cover of what? So I want to start with y, a Riemann surface. So I have a complex structure on y. But then I say, forget about the complex structure of y. It's there, but I don't want to consider it. I want to take a finite number of points of y out. I want to give you a covering by some topological surface x, some non-compact topological surface x. Right? And then what Riemann's existence theorem tells me, there's a unique complex, there's a unique compact Riemann surface that you obtain from x by adding a finite number of points with a unique complex structure that will make this topological cover into a map of Riemann surfaces. Okay, so really what this means, unpacking all of this, is saying, well, maps of Riemann surfaces are ramified covers, but really ramified covers, once you decide what complex structure you're in y, are maps of Riemann surfaces. Because it's not possible that you can endow a ramified cover with 27 different complex structure above it so that it's a map of Riemann surfaces. Okay. So Riemann's existence theorem tells us that if you want to count map of Riemann surfaces, you may as well count map of ramified covers. So the problem that is born in as an analytic problem is actually a topological problem, because count the covers and then slap on y whatever complex structure you want to slap, and you get the correspondingly the number of maps of Riemann surfaces is that same number. Okay? And so how do we count number of topological covers? Ooh. You use what's called the monodromy representation. And so let me draw a picture for you of a map of Riemann surfaces here with its branch points. And then what I'm going to do is I'm going to pick a point which is not a branch point. Call this x naught. And because x naught is not a branch point, it has the inverse images, exactly the inverse images, and I'm going to label them. Right? I'm going to label them 1, 2, 3, 4, 5. Okay. And then what we can do is we can take any element of the fundamental group of y minus the branch locus. Right? So for example, I can take a little loop winding around the branch point exactly once. And what I can do is I can lift this loop starting at any one of these inverse images. Right? So what happens is while this loop has to start in one of these 5 inverse images, has to end in one of these five inverse images, but it does not have to end in the same place where it started. Right? That will depend on the kind of ramification profile you have here. Right? So you, for example, if you lift the loop starting at 1, you may end up at 2. If you lift the loop starting at 2, you may end up at 3. If you lift the loop starting at 3, you may end up back at 1. And maybe 4 and 5 do this. Okay. So what have I done? I've lifted this loop at 5 different starting points, and then getting correspondingly 5 different endpoints. So what's that? That's a permutation of the index set 1 to 5. Right? So what I'm getting is I'm assigning to this element of the fundamental group of the puncture Riemann surfaces a permutation in S5. Now, again, if you've never seen this before, lock yourself in a room with a cup of coffee and a cup of chamomile and meditate, and it will become, after a while, instead of being confusing, it will be obvious that this assignment actually determines a group homomorphism between this fundamental group and S5 in the permutation of 5 letters, right? Because of how the operation of the 2 groups are defined, right? And so what we're getting is that every time you have a cover, you get an equivalence class of group homomorphism. Let me call it phi sub f is a group homomorphism from the fundamental group of y minus the branch locus based on x naught into SD. And what is the equivalence relation? Well, the equivalence relation is that we introduced an additional structure that was not part of the original data of the cover, which is we labeled these 5 points. Right? So you could I could have labeled them 1 through 5, right? And Jay walks up and is like, I don't like this numbering. I like to start 1 up top and go 5 down. And I say, Jay, you're a strange person, but okay, that's fine. That's perfectly, legit. What happens is that my monodromy representation and J's monodromy representation will differ by postcomposition with an inner automorphism of SD. Great. So what we're really counting is inner automorphism classes of monodromy representations. How many different monodromy representations are in one inner automorphism class? Well, typically, generically, d factorial, right? Because I have d factorial ways to label these inverse images 1 to 5. But if this cover has automorphism, I could have fewer than d factorial, because different labelings might give me like, representations that are actually connected by, for coverings that are connected by an automorphism. But here is why it's naturally important from this point of view to divide by this out f. Because if you actually count these covers divided by the out f, this is really counting this monodromy representation always dividing by d factorial. Because d factorial is either going to count the number of monodromy representation, or actually do the division by automorphism as well. So let me. Oh, sorry. One more thing that I'm almost forgetting, right? So let me say that this is rho sub P1. Little loop. I have a little loop that winds counterclockwise once around a branch point, right? And this P1 is a branch point that is carrying together a ramification profile of type eta 1, right? Which, in this particular example that I've drawn, would be 3, 2. Right? Because the ramification order here determines actually the number and the length of these orbits, right? In the of the action by composing this loop with itself a bunch of times on the points 1 through 5. So I guess what I'm saying is that rho P1 will be assigned to a permutation sigma sub rho sub P1. It's really fun in LaTeX, right? That has cycle type. Has cycle type eta 1. Okay, so let me write a second, either another definition of Hurwitz numbers or a theorem, depending on what you want, right? But this is the number of monodromy representations, phi from the fundamental group of y minus the p's and the q's based at some point x naught to SD, such that phi of rho p sub I has cycle type eta I, and phi of rho sub q sub j has cycle type, is a simple transposition. Okay, and we're counting this monodromy representation simply divided by 1 over d factorial. Okay. I'm waiting for Alessio's objection. Okay, so Alessio would be like, okay, where is your connected, disconnected thing here going, right? So from this perspective, this is the natural definition that stops here, counts disconnected covers. If you want to count connected covers, let me put in a different color. This is for connected. If you want to count connected covers, then what you also want to ask is that the image of phi acts transitively on the set 1 to D. Okay, because acting transitively just means that, you know, each of these images of a loop downstairs provides you with a set of elevators, right, that connects the various floors of this Riemann surface mall, right? And you're connected if you're able to find elevators that bring you from whatever floor to whatever floor, right? So the row P1 elevators do not allow you to go from floor 1 to floor 5. It only allows you to go 1 to 3 and back to 1, or 4 to 5 and back to 4, right? So if I only had these elevators, then I would not be able to reach the floors, right? But in this picture, what's happened is that maybe there's some other loop that will give some other sets of elevators, right, that then will connect all the floors, right? And again, the algebraic way to state this is precisely that the image of this group of homomorphisms in SD acts transitively on 1 to D. And one more variation here was, well, really, this is not going to keep track of this labeling of these points. So if you really want to label those points, you need to take the product over the automorphism of eta I. Again, there's an annoying amount of details that on a first run through you can very well ignore, right? But let's do a couple examples. Let's see how much time do I have left. Okay, 15 minutes. Yep. All right, so a couple examples. Because now I can really count a lot of stuff. Well, not really, but a lot more than before. Right, really the one example that I want to do is h 0 to 0, degree 3, 2 maybe, 2, 1, 2, 1. Okay, and okay, so let's start from the disconnected problem, which is simpler because it has one fewer condition, right? So here what I'm counting is 1 over 3 factorial. These two permutations do not have any automorphism, so the product of the automorphism is, 1 times 1. I don't care. Right? And then I want to count the number of monodromy representations that from the fundamental group of a puncture P1 to S3, puncture at 4 points, right? A fundamental group of a puncture Phi1, puncture at 4 points is a free group on 3 generators. But you can also think of it as generated, if you want to make it more symmetrical, it's generated by little loops that wind around each of the punctures, subject to the relation that if you compose all these groups, you're winding up over all the punctures, then you can push the rubber band around the world and pull it back, and it's trivial. Okay? So really finding a monodromy representation is finding 4 transpositions in S3, right, that multiply to the identity. But in S3, we have this really, great simplifying thing that the transposition is the only odd permutation. There's no other odd permutation. And so if you take any three simple transposition, their product has to be a transposition. So you're actually free to choose the first three things freely, and the fourth one is determined. And how many transpositions do we have in S3? We have 3, so 3 times 3 times 3 is 27. Right? So there's really 27 divided by 6 covers. And this is, this is a funny number. This is 4.5. Okay, so there's 4 1/2 covers, disconnected covers. Now let's think about a little bit if we're doing the count of connected covers. We want to say, well, we want these 4 transpositions that I chose to generate a subgroup of S3 which act transitively on the label 1, 2, 3. Well, the moment that you take 2 distinct transpositions, you generate all of 3. So that certainly acts transitively. So the only situation in which this is going to fail is if you pick the same transposition 4 times, right? 1, 2, 1, 2, 1, 2, 1, 2. Then the subgroup generated is cyclic 1, 2, which does not allow you to reach, right? The people on the 3rd floor of the mall, they live an isolated life, never being able to get in or get out, right? And so what we need to throw away in this case is the 3 possible choices of always the constant choice of 4 times the same transpositions, right? So in this case, this is 1 over 3 factorial, 27 minus 3, which is 24, and so this is 4. Okay. And so what this is saying, right, is that really we have 4 connected covers and 1 disconnected cover. This disconnected cover will be from a curve of disconnected curve of genus 0, right? So it will have a genus 1 component and a genus 0 component. And the genus on that disconnected curve, you have sum of the genera, and then you subtract 1 for every excess component beyond the first one. So this is the right thing to consider genus 0, even though it feels weird. If I had written 2 rational curves, that would have been genus minus 1. Okay. And this is a map from an elliptic curve to P1 that has a hyperelliptic involution. So it has, in particular, an order 2 group of automorphisms. That's why it counts with 1/2. Okay. Again, if this is the first time you're seeing this is probably a lot, but that's what this afternoon and the next 2 weeks are for, right? So this is, again, a little example of how much more algebraic and computational the problem has become. Okay? All right, so in the last 5-7 minutes or something, I want to go just a little bit beyond in this idea of connecting the Hurwitz counting problem to the representation theory of the symmetric group. And let me make a small simplifying assumption. Just the complete version is in the notes, but let's assume that we're going to do disconnected Hurwitz numbers, and let's also assume that G is equal to 0. Right? So in particular, the fundamental group of the base curve is now a free group, and that allows me to give like a simplified version of the statement. Right? Then the Hurwitz number H to 0 other than its product of the automorphism I is has another nice formula, which is it's C, let me write it this way. So it is the product of C sub eta I times the product 1 to R of C sub T. And then I look at the coefficient of C sub E, and like, what are you talking about? What are these things, right? So these are elements, these are vectors in a particular algebra, right? Namely, the class algebra of the symmetric group, right? So let me introduce that. So Z, so the Z of SD, by definition, this is called the, well, is the center of the group ring of SD. This is called the class algebra. And if you're not familiar with this, well, think of it as a vector space with a basis. Let me say C sub eta I. Eta I is a partition of D. This is a, well, whatever your field you want, it's a K basis. Right? And what is C sub eta I is a formal linear combination of all elements of SD with cycle type eta I. Right? So let me, again, if you've never seen this, then the thing to think about is one example. Right? So C of S3 is a three-dimensional vector space. Right? It has a vector that I'm going to call C sub E, which is just the identity element. Then I have a vector that I'm going to call C sub 2, 1, and this is 1, 2 plus 1, 3 plus 2, 3. And then I have another vector that I'm going to call C sub 3. And this is 1, 2, 3 plus 1, 3, 2. Okay. So right now it's just a weird vector space because it's a finite dimensional vector space, and I've given funny names to a canonical basis of this vector space. But these funny names allow me to give this vector space a natural multiplication, a natural algebra structure, right? Because how do I multiply two elements like this? Well, I know how to multiply individual permutation in the symmetric group because it's a group. And then I know what bilinearity means, and so I can go to town and I can multiply anything, like you can tell a high school student in the US, right? Without having any idea of what they're doing, you can tell them FOIL, right? And they're going to actually compute this, right? But so this is an algebra, and because of the fact that we're lumping together all sort of orbits by the conjugation action on this all elements in an orbit of the conjugation action together, then this multiplication is commutative. Okay, you can think about it, but if you swap things, you're going to permute the element that you're getting in the solution, but you're always getting the same elements. Okay, and so this is a commutative algebra, and so what does it really mean to take this product in this commutative algebra? Right? Well, foil, 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 foil until you're exhausted and on the ground, right? And then what do you see after you've foiled everything? Like the monomials, so foil but don't multiply in the group ring, right? So just do this formal foiling, right, here. And what you see is R plus S tuple of elements in the symmetric group with prescribed cycle type. And then you say, well, but now I only want to keep those that multiply to the identity. which means, well, now do the multiplication and only look at the coefficient of C sub E. Okay? And so, cool, that seems like another sort of weird restatement of the Hurwitz problem. But let me just conclude today by saying that algebraists have studied this object quite a bit and combinatorics quite a bit. And in particular, there's a classical theorem by Maschke that says that this algebra is semi-simple, which means there is a basis, not this basis. This basis, the multiplication is pretty complicated. But there's another basis in there such that the multiplication is semi-simple, which means that EI times EJ is 0 unless J is equal to I, and then EI times EI is EI. So the multiplication is very simple. So what one can do is change bases, and then this multiplication problem becomes very simple. Now, what's the catch? The catch is that the change of bases is also well understood, but it's in terms, the matrix of changing bases is exactly the character, exactly, no. There's some, little combinatorial crap here and there, but it's fundamentally the character table of the symmetric group. Right? So if you know the character table of the symmetric group, then you basically can reduce the Hurwitz counting problem to a very simple problem of, in this algebra. Right? And so this gives rise to what are called the Burnside formulas for Hurwitz numbers. They're actually nice, close formulas, but in terms of characters of the symmetric group. So Hurwitz theory for a group theorist is nothing other than character theory for the symmetric group, which is, again, to me, it's like a really cool translation. So let me stop here. Like I said in the notes, I'm not going to talk more about this classical stuff, but there's more than I said in the notes. So feel free to chat me up if you want this afternoon or any other time.